So we have already discussed moment of inertia of three different objects. It's a rod, which was one-dimensional, a disc, which was two-dimensional, a sphere, which was three-dimensional. We are again taking another three-dimensional object, but we are viewing it differently. What we are going to discuss today is the case of a cylinder. This is a cylinder. Okay. Now, considering this cylinder, this is going to be your axis. This is how you are going to consider the suspension of the cylinder. So when this is going to be the axis, actually, it is the length of the cylinder that matters. That is going to have a say on the moment of inertia. Okay. So more is the length, more will be the moment of inertia. Less is the length, less will be the moment of inertia. So though it is a three-dimensional axis, we are only going to consider the length here, because as I said, it is the length which is going to have a say on the moment of inertia. So let us go into the derivation now. Right. So we shall start with the derivation for moment of inertia of a cylinder. So now let me consider a cylinder. I'm considering a cylinder, okay, of mass m and length L, and this is going to be my axis. My axis is to the center of the cylinder. This is how I'm going to suspend, and the cylinder has a radius r. Okay, that is one thing. So now mass per unit length. As I keep telling you, I am bothered only about the length of the cylinder. So mass per unit length m is equal to m by L. That is the first consideration we are going to do. Mass per unit length is m by L. So now I am going to take this cylinder and keep chopping it. I'm going to take this cylinder and assume that I have the cylinder made up of various portions, which means I'll end up with a lot of discs. I'll end up with a lot of discs. So let me consider any one disc here, okay? Any one disc here, and let us say this has a thickness of dx, and it is at a distance of x from the center. So I will say mass of this elemental disc, the small disc, is equal to m into its thickness dx. That is the first thing. Then what should I find out? I should find out moment of inertia of the disc through its own axis. What do I mean by this own axis? See, now this cylinder, when I say this is how I'm going to suspend. So when I'm going to suspend like this through a disc, now I have the disc here. Okay, I have the disc here. If I'm going to suspend it like this, own axis is going to come like this. If it is not own axis, it will be like this. So I need the moment of inertia of the disc through its own axis. So recall the perpendicular axis theorem, where the own axis would amount to the ixx and iyy. So if it is own axis, your moment of inertia was actually mr square by 4. That is what we are going to write now. So our mass here is m into dx into r square by 4. Okay, so this is the moment of inertia m dx into r square by 4 when I have the axis here. But my axis is actually here, and initially I wrote for an axis which was here, but my axis is here, and you can see both these axes are parallel to each other. So to find the moment of inertia through this axis, you can take the moment of inertia through this and use parallel axis theorem and add up on this. So moment of inertia of the cylinder, okay, because of dx at AB, because of dx, cylinder at AB because of dx is actually now given by m into dx r power 4 by 4 plus m into x square. Sorry. So how we should go is mass into the distance, right? So m, this is the mass is m into dx into x square. So m dx r power 4 by 4, m dx into x square is the moment of inertia because of this. Now, but my cylinder is not made up of only one disk. It is made up of numerous disks. So find the moment of inertia of the cylinder due to all the elements. What do? Yes, I integrate I integrate, and what are the terms? M r power 4 by 4 into dx plus m x square into dx. And what are the limits? My cylinder is of length L, but I'm taking the origin here. So this would be minus L by 2 and this would be plus L by 2. So my limits are minus L by 2 and plus L by 2. Like every time I'm going to change it to 0 to L, and I'm going to take, which means I'll have to write 2 here, and I write minus L, sorry. When I write 2 here, this would become 0 to L by 2 m r power 4 by 4 dx plus m x square into dx. Now I'm going to split it into two different terms. So I would get actually m r power 4 by 2 0 to L by 2 dx, which is the first term. 2 and 4 to get cancelled. Same m r power 4, since it's a constant, I'm taking it outside. M r power 4 by 2 into dx plus again 0 to L by 2. I can take the 2m outside here, and it's going to be x square dx. Am I right? Now let us integrate this. M r power 4 by 2. What do I get here? X between the limits 0 to L by 2 plus 2m x cube by 3. Again I get 0 to L by 2. So now let us apply the limits. Okay. So what do I get here? Moment of inertia of the cylinder as m r power 4 by 2 into L by 2. This is the first one, plus 2 by 3 m L cube by 8. Am I right? So when I apply the limits here, I'm bringing 3 outside here. I'm sorry. Yes, I'm bringing the 3 here outside. L x cube is L by 2 the whole cube. So I would get L cube by 8. So I know my small m is equal to m by L. Substituting that, what can I get? M by L r power 4 by 2 into L by 2 plus, why did I put r? I'm sorry, this is not r power 4. I stand corrected. This is r square. Please correct it everywhere. It's not r power 4. It is r square. I don't know why I wrote r power 4 here. So everywhere it is going to be r square. Just correct it. Sorry for the earlier lapse. So this is going to be again r square. R square. If you noticed it earlier, good. So again, this is r square. R square plus 2 by 3. Again, here I have to write m by L, L cube by 8. So what do I get here? My L and L get cancelled here. So I am going to get m r square by 4 here, plus here what do I get? This L cancels with this, I get 2, and here I get 4. So what do I get here? M L square by 12. Okay. So what do I get here is, for moment of inertia of a cylinder through this axis, I get m r square by 4 plus m L square by 12. Excuse me for the earlier lapse. This is r square, not r power 4. So this is moment of inertia of a cylinder when I take the axis like this. So you may now question me, can't I take an axis like this? Of course you can. So now let us discuss that case. That's a very brief case. So moment of inertia of a cylinder along its axis. Okay. So now when I take like this and take the axis like this, actually my axis is passing through numerous disks. My axis is passing through numerous disks, and I have a case where I have a disk here and the axis goes like this. We call perpendicular axis theorem. So for a perpendicular axis theorem, when it passes like this, the moment of inertia of one disk is given as m r square by 2. This is the relationship we derived for axis passing through the center. So, but I have a lot of disks. In a cylinder, I have a lot of disks. So moment of inertia of cylinder when the axis is like this is equal to, obviously it's a summation of all the disks. So it's going to be sigma, sorry, it's m, small m, sigma m r square by 2. That's it for a moment of inertia of the cylinder along its own axis.